Today we're going to talk about section 9.1. Section 9.1 is, there's one new thing, but the rest of it is review. So 9.1, and you should have the notes and be following along with them. So factorial. Factorial, first thing is 0 factorial, we define it to equal 1. So we're going to work on reducing factorials. So suppose I have something like 10 factorial divided by 8 factorial. Well, really, that's 10 times 9 times 8, etc., all the way down to 1, divided by 8 times 7 times 6, etc. So we can see these factors will divide, and we're going to be left with 10 times 9, which is 90. Great. Well, we're going to be using more in this chapter are things when we're looking at what about n plus 2 factorial over n factorial. Okay. Well, we just need to remember what the definition of factorial is. We're going to start with the number that we have and multiply it by one number less than that, which would be n plus 1, and then one number less than that, and one number less than that, etc., until we get down to 1. So for n, we'll start at n and multiply by n minus 1, n minus 2, etc. I would recommend write out a few terms so you can see correctly how they reduce. So this reduces to n plus 2 over n plus 1. So that's the first thing. We're going to review our factorials. The second thing is a sequence. You can see on the sheet, a sequence is a function whose domain is the set of positive integers. And we write our sequence in the form a sub 1, a sub 2, a sub 3, etc. So the domain meaning 1, 2, 3, those are all integers. We could start at n equals 0 if we want, but we would need to specify that. By default, we're always going to start with n equals 1. So our objective is to write the nth term of a sequence. So suppose we have this first example, 1 over 2, 1 over 4, 1 over 8. Well, I know the nth term will be 1 on top, and what will be on the denominator? So we can look at things like, this is when n is 1. This is when n is 2. This is when n is 3, etc. Now, we want to get in the habit of recognizing some powers, arithmetic sequences, geometric sequences, and factorials. This one I notice are powers of 2. 2 to the first, 2 to the second, 2 to the third. Well, look how that nicely corresponds to my n. So the nth term must be 2 divided by n. So we can express our sequence in terms of the nth term. Well, let's look at the next one. 4, 9, 16, etc. divided by, oh, I forgot the 1. I'm going to write it as 1 over 1 so that we're consistent. All right, so let's look at, what do you notice about the numerator? The numerator are powers, they're perfect squares. 1 squared, 2 squared, 3 squared. So it ends up, it is n squared. I'm going to put this down here just to remind me so I can make it easier to check. Now, the denominator are the odd numbers. Maybe you remember how to express odd numbers in terms of n. Maybe you notice that I'm adding 2 each time. Well, that makes it arithmetic. You may remember from last year that any arithmetic sequence can be expressed like this. And if you had me for pre-calculus, you would remember that any arithmetic sequence is something linear, which is like mx plus b. Up here we called it a sub 0, because b, the y-intercept, is what happens when x is 0. So once I figure out what my constant rate of change is, I know that's going to be 2 times n. Now I have to figure out what was a sub 0. You could think of it, well, what would have come before 1? Well, if I'm adding 2 every time, negative 1 would have come first. You could also think of it, just once you know that it's 2 times n, we'll plug it in. 2 times 4 is 8, but I wanted 7, so I need to subtract 1. Check it. 2 times 3 is 6, minus 1 is 5. It does work. Therefore, I have my nth term. Now, we will want to also get in the habit of noticing factorials. So 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial, etc. That's going to come up later on. We're going to see that more and more. Why would I think factorial? What do you notice is happening? I multiply by 2, and then by 3, and then by 4, and then by 5. So I'm going to think here n factorial. And the last example on the sheet, we have 1 over 2, 2 over 3, 3 over 4, 4 over 5. So if this is when n is equal to 1, and this is when n is equal to 2, etc., you'll probably notice, well, the numerator is just n. And what about the denominator? It's just 1 more than the numerator. And there we have our nth term. Okay. Now, if we want to determine, we're going to be asked, does the sequence converge? If we want to figure out, does the sequence converge or diverge, that's letter C here, we are going to find the limit. So I want to know, does this sequence of terms, are they going to converge to something? And you may, okay, so it's going to be 5 over 6, 7 over 8, 100 over 101. What is it converging to? Well, let's take the limit. As n approaches infinity of n over n plus 1. That limit is 1. Therefore, this sequence converges to 1.